So we're going to undo the chain rule. And I don't know if you remember when we did the chain rule at the very beginning, we did a little bit of substitution. And then I think I actually had, and Mr. LaFrance, both of us had in our notes, this method sucks. And then we never used substitution after that again. I don't know if you remember. It's not very often that we have actually in our notes, this sucks. But we did. But when we undo it, we do need to use substitution. Sometimes the chain rule, you could maybe just see and not have to use it. But often undoing the chain rule involves a lot of mental math manipulations. That substitution really, really makes sense. Okay? So this is what your eye has to start looking for. You will know to use the chain rule when you see the derivative of the inside function also in the function. So what do I mean by that? Well, let's start looking at a couple of examples. Here's one from our notes when we did the chain rule. So if that's the derivative and you had to work backwards, do you see that it was a chain rule originally? Because we have, and I'm going to highlight things here, we have in yellow the inside function, and we have in green the derivative of that inside function happening right after. That's classic chain rule stuff. So this one would be like, oh, I can see you brought the 5 out in front, then you multiplied by the derivative of the inside. So it's really obvious that it was this, and add a plus c there. In this question, you wouldn't have lost a mark if you didn't have the plus c, because the question said find a function, not all of them. So plus 0 is 1, and that would be okay. But what's going to happen when we do lots of integrals is they won't work out perfectly. Like this one worked out perfectly because it had the 5 out in front. But if it had a 7 out in front, and instead of 6x plus 5, it had 12x plus 10, things would sort of be a little bit off. So we're going to have to use some techniques to help us when those things are a little bit off, so we don't have to struggle with the mental math. So I'm going to use this color coding a lot, okay? And you're going to get some tough integrals, and now you're going to have in addition to this purple sheet where you're like, I've got all of these integrals memorized and ready to go. You're now going to have in your toolbox, I might have a chain rule. So I should also look for derivatives inside of integrals. So can I see an inside function? And do I see its derivative in the same equation? So in the first one, I see x squared minus 7. That is inside the power of 4. Its derivative is 2x. This is going to be one that has a chain rule that we can undo. The second one, inside function x squared minus 3x. Its derivative is 2x minus 3. We could use the chain rule to do that. The inside function is sometimes on the bottom of a function. If this is on the bottom and the derivative is this, okay? Right? Looking at this initially, most of you probably don't see natural logarithm. And that's why our substitution is going to be really important. Did anybody like this scream natural logarithm to you at the moment? No. But it's going to be a natural log. Okay? Here, we have tan x inside of sin x, and its derivative is secant squared. This one's missing the dx, you can add it on. So in each of these, I've highlighted the inside function in yellow, and its derivative in green. And sometimes its derivative doesn't have to match up perfectly. Like you might get one like this one, but instead of having 3e to the x here, they play around with the coefficient and leave it as 8e to the x. And it's not a perfect match, but close enough. And if it's close enough, we're going to be able to figure out its integral. Like what's the derivative of sine 2x? It is cos 2x, but it would also have a times 2. So this is one that's not quite matching up perfectly. That last one's actually a lot of fun. Here it is formally. Okay, and I'm going to color code this so we can connect it to what we saw informally with all of those examples. You have an integral, and you notice in yellow, there is one function inside of another function. And you also notice in green that the derivative is there. And I don't know who decided that U was the best letter to use for substitution. Probably because it's kind of funny when you say the integral of fu du, maybe. I'm not sure. Added some humor to calculus. But what happens is you let u equal gx, then the derivative of u with respect to x is just the derivative of gx. And then here is something, again, calculus gets a little bit interesting. Du dx is Leibniz notation for the derivative. And yet in Leibniz notation, because du is like little change in u over little change in x, we sort of can rearrange things and get the du by itself by multiplying both sides by the dx. Even though du dx is technically just one thing, it's the derivative, we sort of break it up and move the dx over to the other side, and then we can do a substitution. Notice that this part gets substituted out for a du. And u replaces the g of x. And what the substitution does is it changes a complicated looking integral that might have some complicated mental math involved with it into a simple integral that still has mental math, but it's much easier to deal with. So, how do we do this? Some of these you could probably do already, straightforward, but we're going to look at the technique because the technique actually is really nice for working backwards. So our startup is you look for that inside function and let u equal that inside function. Find its derivative, du dx, and then get du by itself to be 2x dx. Then we can go back to our original integral and substitute everything out. So instead of the yellow, x squared minus 7, you replace that with u. You still have the exponent of 4. The 2x dx gets replaced with the du. And now you have a simple integral. It's just a power. What do we do with powers? Add 1 to the exponent and divide. Does it make sense that you would get u to the 5 over 5 plus c? And now we can substitute back. And we've got the actual integral. By trying to, like this one, I think you could have done directly. But sometimes you miss out on like the number divided by 5. You might forget that, make simple mistakes. So the substitution just helps us avoid some of those simple mistakes. Question, yes?
Why don't you have to divide by the inside?
Because it has, like, if we take the derivative to check, right? if I did the derivative of my answer to check, the 5 would come out in front, cancel out that 5 on the bottom. Subtract 1 from the exponent 4, and then I'd have to multiply by 2x, which matches up perfectly with what I started with. Now, everything so far that we've done with chain rule has always been a nice number where you just divide by that number to compensate. But we haven't been able to do anything when the inside is an actual function, because if you divide by the function and then you check, then you run into your quotient rule and it makes a whole new problem. Okay? So the integration by substitution only works if you have an inside function whose derivative has an x, and you see that type of function on the outside. And by type of function, this question would have worked if we had 2x, 5x, 17x, negative 32x, any kind of x, it could have worked. And we'll get to ones like that eventually. To start off, though, we're going with ones that work out really nice. Like this one works out really nice because I see the natural log of x. The derivative of the natural log of x, so if I make u my natural log of x, the derivative is 1 over x. So I can get du by itself by writing x to the minus 1 dx. So that means the yellow part can be replaced with u, and the green part and the dx can be replaced with du. And again, you just get this simple looking function. Add 1 to the exponent, divide, plus c, and then substitute back. So try C and D, and then we'll do E together, because I like E. Yeah, you do that one. Yeah. All right, let's see how you did. Because it's a 1/3, right? Adding 1 to the exponent and dividing, just dealing with fractions gets a little bit messy. So the substitution just really clears that up to see that that's what you would need to do. So again, noticing the inside function, letting u equal the inside function. And d. This just is 5e to the u. That is about as easy an integral as you can get because that's 5e to the u plus c, and then substitute back. Now some of you are probably thinking, oh, but if I can see it right away, do I have to do all the substitution? Technically no, but I think with the amount of ones that get complicated with the mental math, doing the substitution will just be almost as fast, if not faster, over the long run to do it all the time. Because you just sort of get into a mode of, oh, it's substitution. And then you can do the easy ones or the hard ones either way. Okay? I think this next example is one that is a little harder to see the substitution part. You might technically go through some of our other strategies that we've used so far, like think, oh, could I factor something? Can something simplify? Can I rewrite this in a different way so I can use my simple rules? So your brain might try different techniques in this one. But if we do see that, okay, there's a relationship between the top and the bottom, the top is the derivative of the bottom. So what happens, I don't know if it's going to work, and this is sometimes what happens when you try substitution, is you're not sure that substitution is going to work, because it doesn't feel like you had an inside function like the other ones, right? The other ones, the yellow part I highlighted, was always inside of power or inside of another function inside of E. But when I do this, and I let U equal that, and I find my derivative, and I do my substitution, so I change that, I get a U to the minus 1. Or you could have kept it as 1 over U, but either way, you're going to get the natural log. Because the integral of 1 over U is the natural log. And then when we substitute back in, technically I should have absolute value bars around that. I get the natural log of x cubed minus 5x. Okay, I'll let you try F and G, and then I'd like to do H together, because H is fun. So we notice, I mean, it's kind of, on this one, if I show you, the highlighted part kind of gives it away. But that's your U, there's your du, you do your substitutions, and you just have cos u, integral of cos u, positive sine u plus c, substitute back. And again, anytime with integration, especially the indefinite integral, you want to check something, do the derivative. In fact, I encourage you to do the derivative because you need to know all your derivative skills for the exam anyways. So by doing the derivative to check, you're just sort of keeping those skills up to date. And here's G. Tan is inside of sine, so that makes sense to make that your U. Derivative is secant squared. This is missing the dx, so I should... Did we fix it on yours? Or is yours missing the dx as well?
We have.
Okay. We just hadn't corrected it here. So, sine u, negative cos u, substitute back, and we're good. Nice. Oh. This one is fun for me. This one's fun for me because it doesn't quite work perfectly, so that's kind of fun. And then it's fun for me because I can do it in more than one way, get completely different answers each time. This is hard for the brain. Completely different looking answers, which are all right. Which is kind of weird. So, start off, I could, because I have it highlighted in yellow, I could let u equal sine 2x. But then when I do the derivative, do you see that it has a chain rule? And it's like, it doesn't match up because of that extra 2. But what I can do is I can move the dx over and move the half over to the other side, because then this matches up perfectly with this. But when I do my substitution, it means I have an extra half in there. But if I have that extra half in there, that really doesn't make things too hard. How do we do simple integral? Well, that half would stay out in front. We'd add 1 to the exponent and divide. So you would get u squared over 4 plus c. And now I substitute back. And my first answer that I get for this question is sine 2x squared. Could have put the squared in between the sine and the 2x if I wanted. over 4 plus c. Method 2, just because it's fun. Instead of letting u equal sine 2x, is it not true that the derivative of cos is sine and sine is cos? I mean, there's a negative involved, but I could have made my u cos 2x. Well, what would du dx be? Well, the derivative of cos is negative sine, keep the inside the same, chain rule, multiply by the inside. And now I would get negative 1/2 du is equal to sine 2x dx. Very similar. Obviously, I'd recommend the first one we did better because it doesn't involve a negative, right? Anytime you add a negative into a question, your chances of a mental math mistake just go up like crazy. So the first method is definitely better, but we could have done this. And now when I substitute, I would get u negative 1/2 du, which, with that negative 1/2, add 1 to the exponent and divide, plus c. And I get negative, and this time it would be cos squared 2x divided by 4 plus c. Which is not the same as sine 2x over 4 squared plus c. These are different. Interesting. Method 3. This is where integration gets messed up. Method 3 uses the fact that you know that sine 2x is 2 sine x cos x. So in my question, I have sine 2x cos 2x. What would that be equal to? Can you see that if you had sine 2 times 2x inside, this would be sine 4x, but I would need a 2 out in front. I don't have that 2 out in front, so I could put it on this side as divided by 2. You can play around with your identities. I'm sure that's what you wanted to hear. And I could change this integral of sine 2x cos 2x dx to sine 4x over 2 dx. What's the integral of sine? Negative cos, so I could have negative cos 4x over 2, but this is a simple chain rule, right, where you multiply by 4. How do we undo a simple chain rule of multiplying by 4? Divide by 4 plus c. So now we got one answer with sine squared 2x over 4. We got another answer with cos squared x 2x over 4. Now we got a third answer of a cos 4x over 8, which is like completely different. Like the first two look similar and you almost feel like, I bet you there's an identity that makes them the same kind of feeling. But this looks completely different. And it is. But it's also a right answer. Now don't just go and say, oh, Mr. JR, I noticed in our notes you came up with multiple different right answers that look different. So here's my answer to this question. It's right. You just have to figure out the method I used. No. It's not going to work out. So I think this one is fun just because you have different options. Okay? Whenever you, things to look for. Okay? I definitely would use substitution method number 1 is my favorite in this one. I think it's the most obvious. But we're going to have to, in integrals, start looking for substitution now. Do we have a function and its derivative in the same integral? Then we can use substitution. But whenever you have sine and cos beside each other, multiplied, you should also get triggered into your double angle formula. 2 sine x cos x. The 2 doesn't need to be there because you can just move it to the other side if you wanted. I could take this 2 and move it over here and have 1/2. Right? You can make a new identity that way. So whenever you have those 2 multiplied together, you should trigger, oh, I also have an identity I could check. Because what happens in advanced calculus is usually you run into something, and you'll see this on your take-home quizzes. Probably noticed this already. You're like, oh, I don't know how to do this. And you have to go into problem-solving mode and say, well, what do I see? And you might try something, and it might not work. And then you'll be like, what else do I see? Try something else. You're like, oh, this worked. And you show it to your friend, and your friend is like, how did you come up with that? Well, you might not have come up with it right away. Problem solving is exactly that. Trying something, it might not work, then trying something else. But being sort of a little persistent and seeing, what else do I know? What else could I try? Okay. Here's another one. We have 4x squared plus 1 inside e to the x. But what's its derivative? Its derivative is 8x. But we don't have an 8x. But we do have an x. So we sort of, in substitution, the coefficients don't really matter. And we'll find that out here, because if I let the u equal the 4x squared plus 1, then when I take the derivative, I get 8x, but that coefficient I can move to the other side and make it 1 over 8. I might even rewrite this so that my x dx is together.
Morning.
So my substitution becomes really obvious. I get e to the u times by 1/8 du. That 1/8 can just be out in front. And then we can substitute that. Generally, okay, someone might say, could I get a similar result if I just made the u the 4x squared? The answer is yes, you can try it. But if you have an inside function, it usually makes sense to make your u all of the inside function, not part of it. Making your u part of it sometimes works, sometimes causes headaches. In this case, making it all of it, the derivative of that 1 just goes away. Life is straightforward and easy. But it could have worked in this case if you just let u equal the 4x squared. But the recommendation is whatever you use the substitution for, you make it for the whole of the inside function. Usually works the best. So now we're getting into ones where the inside function doesn't match up perfectly, but the only thing that doesn't match up is the number in front. Because like the yellow part, what's the derivative? Negative 8x cubed. We don't have the negative 8x cubed, but we do have the x cubed. So as long as the function matches up, the coefficient won't matter, because if we do the substitution, we can rearrange it with that coefficient just to get the x cubed dx. If you watch YouTube videos on this, sometimes people do this as a technique, okay? I've seen this technique. Some of you, if you like this better, you can, right? Someone said, but I wanted a negative 8x cubed, and I have an x cubed, right? Because the du is negative 8x. You really wanted it to match up. So what people do is they say, well, I'll put a -8 there. Well, that's not really allowed. Unless I also divide by 1 over -8. And then when you do the substitution, can you see that this becomes your du? This becomes your u. And you still have the -1/8. We got the -1/8 because we substituted in and included it in the substitution. This gets the -1/8 because you did preliminary work to make it match. Both are fine. But just in case you see that other technique, because I know that you guys are just watching math videos every evening all the time. It's like oh, my TikTok feed.
It's addiction.
It's addiction. It's Instagram. That's what you look the longest on when you're going through Instagram. So they just keep feeding you that. I know that's exactly what you see every night. Oh. Just kind of makes me think creatively, like, you know how they don't necessarily design it to be addicting, because then they could run into legal trouble. But sure it feels that way. Could a culture slowly manipulate their social media so everybody in that country becomes way smarter than everybody in other countries? A sort of positive manipulation, right? Because you're being manipulated. We all know that. We're all being manipulated right now. Mainly you're being manipulated so people can make money. That's the main way that people want to manipulate you, right? I want you guys to all be phenomenal students. I'm trying to manipulate you this way. Because if you're phenomenal students, I think you'll get a really good job. And if you get a really good job, you'll contribute to the economy, and my pension will be safe. Right? That's my manipulation. So I do my u is 4x cubed minus 1. I see that as it's on the bottom. I include the -1 because I'm like, I want to include all of that. So my bottom becomes really straightforward and simple. But my du gives me a 12x squared. I want a 5x squared. Or, okay. So I got the 5x squared by multiplying by 5/12. I don't mind that. I also don't mind if you just did this. Okay, we'll talk about this. I like the mental math of this better. Can you see that if you had 12x squared, your brain is pretty easy to get x squared by itself? To go from 12x squared to 5x squared, your brain might not like the mental math of multiplying by 5/12. It's not bad. If you think about it for a little bit, you'll say to yourself, actually, that's not too bad to do mental math-wise. But you might like just getting the x squared. If I got the 5x squared by itself, do you see that when you substitute in, you will get 5 over 12 du? If you just got the x squared by itself and replaced it with the 1 over 12, do you see you would have to leave the 5? And then you'd be left with a 5 on the top anyways. So 2 options there for how you want to work with your numbers. But now we get our natural log, put my absolute value bars. And then you get one that's a little bit messed up. This is going to be our first one that we have to get a little bit creative. Do you see that the inside function is 4 plus x? It's inside the square root. So your temptation is to say, I want to make that my u. But then my derivative is just 1. And I have a problem because outside I have an x. So in this example, the typical student tries substitution and then concludes that substitution doesn't work and throws it away. And then gets stuck and says, I can't do this one. This isn't possible. But we're going to get a little bit creative. So we're going to say, well, I have an inside function. I'm still going to make that my u. But I'm going to play with that a little bit later on. If u is equal to 4 plus x, does it make sense that x is equal to u minus 4? Just rearranging that. Okay. You're like, why is that helpful? Well, du is just dx. So normally, what we'd be able to do from this question, and I'll write it off to the side here. Normally, this is all you would think about in a normal substitution is that part. And normally, if I substituted what I have, I would get this, and I have a problem because I still have an x. And this normally says your substitution did not work. But what we're going to do is we're going to use this rearrangement and substitute that x also for u minus 4. And initially we might say to ourselves, good job, Mr. JR. You just changed the letters, but didn't make the question any easier at all. It looks just as hard as it was before. Thanks a lot. But actually, this is easier because we can use our exponent laws now that we couldn't use before. I can distribute this, but I could not distribute this. That's a big X. I'll just erase. Oh, I'll erase too much. Oh, I really erased a lot. And if I distribute it, I'm going to get u to the 3/2 minus 4 u to the half du. Which each of these are simple power rules now. Add 1 to the exponent. That's simple. Simple power laws with fractions. Add 1 to the exponent, divide by the exponent. Add 1 to the exponent, divide by the exponent. And when I divide by 3/2 and multiply by the reciprocal, I just did the mental math. You could get that in 2 steps, no problem. Then I can substitute back. And it's like, oh my goodness. This actually worked. Little note at the bottom, if you made u the square root of 4 plus x, you should try it. It will also work with manipulations. Okay. So this is where your math teacher says, yeah, for this one we just have to be a little creative. And I'm glad I saw it. Someone smiled because you're like, yeah, I know what that means. That means that I won't get this one. And it will be like, I will get frustrated. And I'll have it on the quiz and I'll be like, ah! And I'll need someone to show it to me. Okay? The idea, though, is the more opportunities we see to be creative, the better we get at being creative and starting to see these things ourselves. That was sneaky. All right, one more for you to try on your own. It combines something we did earlier. It has an initial condition. So because you have an initial condition, you can solve for C. All right, let's see how you did. Do your substitution. See that it's a natural log. Plug things in. Here, technically, I should put the absolute value bars in here just to remind myself. But when I write 4x squared plus 1, that's a parabola shifted up 1. It's always positive. I do not need my absolute value bars there as a result. Solve for C.